The MRI scanner weighs 3 tons. It is cooled to -269 degrees Celsius, colder than outer space. It generates a magnetic field 100,000 times stronger than Earth's. And yet, it images the softest tissue in the human body, without a single X-ray photon. No radiation, no ionization, just physics. This is how MRI works. Every proton in every hydrogen atom has a quantum property called spin. Spin is not literally rotation, it is an intrinsic quantum property that behaves like a tiny bar magnet. Your body is 60% water, H2O, 2 hydrogen atoms per molecule. That means your body contains approximately 4.2 times 10 to the power of 28 hydrogen nuclei, each one a microscopic magnet. Normally they point in random directions and cancel out. Place them in a strong magnetic field and everything changes. Inside the MRI scanner, the B0 field, the main magnetic field, aligns the hydrogen nuclei along its axis. But they do not simply point north like a compass needle. They precess. Like a spinning top wobbling as it slows, the proton's spin axis traces out a cone around the direction of B0. The frequency of this precession is called the Larmor frequency, and it is precisely defined by the equation omega 0 equals gamma times B0. At 1.5 Tesla, the field strength of a standard clinical scanner, hydrogen precesses at exactly 63.87 MHz, the same frequency as an FM radio signal. This precision is what makes MRI possible. To generate a signal, the scanner transmits a radio frequency pulse at exactly the Larmor frequency. This is resonance, the same principle as pushing a child on a swing at exactly the right moment. The RF pulse tips the net magnetization from the longitudinal axis into the transverse plane. A 90-degree pulse tips it completely. The precessing magnetization now induces a measurable current in the receiver coil. This is called the free induction decay. The signal decays in milliseconds as the protons lose coherence with each other. This is T2 relaxation. And as the longitudinal magnetization recovers toward equilibrium, this is T1 relaxation. T1 and T2 are different for different tissues. Fat relaxes fast, water relaxes slowly. This difference in relaxation times is the source of MRI contrast. But a signal from precessing protons is not yet an image. To form an image, the scanner must determine where in the body each signal came from. It does this with gradient coils, electromagnets that create small variations in the main magnetic field. By varying the field spatially, you vary the Larmor frequency spatially. Different positions resonate at different frequencies. The signal is then a superposition of many frequencies, each encoding a different spatial location. The data is collected in a mathematical space called K-space, named after the wave vector k. K-space is the Fourier transform of the image. To reconstruct the image, the scanner applies the inverse Fourier transform to the K-space data. The mathematics was available long before MRI existed. Paul Lauterbur and Peter Mansfield won the Nobel Prize in Physics in 2003 for realizing it could be applied to medical imaging. A piece of pure mathematics, transformed into a diagnostic instrument. By choosing different timing parameters, the repetition time TR and the echo time TE, the radiographer can weight the image toward T1 contrast or T2 contrast. T1 weighted images show fat as bright, useful for anatomy. T2 weighted images show water as bright, useful for pathology, because most disease processes increase tissue water content. The result is the ability to distinguish grey matter from white matter in the brain, healthy cartilage from damaged cartilage in a joint, viable myocardium from infarcted tissue in the heart, without a single photon of ionizing radiation. The contrast comes entirely from the physics of nuclear relaxation. Multiple sclerosis. detected as bright T2 lesions in the white matter. Brain tumors, visible because of disrupted blood-brain barrier and edema. Spinal cord injury, assessed without radiation risk. Every one of these diagnoses, impossible without understanding quantum spin, resonance, Fourier mathematics. The physics is not background knowledge. The physics is the instrument. Not approximation, not intuition. Physics. Next on this channel, radiation therapy. How we use radiation not just to image, but to destroy cancer at the cellular level. Targeting. Dosimetry. The physics of cure. The physics is extraordinary. See you there.